So now we start with the theory of the second meeting. I assume that the homework for the first meeting is done. This course follows a historical line that is often the best way to teach didactically also. In the first meeting, I presented you ideas of Bruno de Finetti of the 1930s. Today, I mostly present ideas by Van Neumann and Morgenstern of the 1940s and 1950s. These are all classical ideas. In fact, the first 2.5 meetings of this course only present classical ideas. Behavioral ideas come only in the mid of next meeting. One reason to do is that if you want to understand the novelty of the behavioral approach, there are some things of the classical approach that you should understand well, that maybe you did not always learn elsewhere. Otherwise, no harm repeating. So that's one reason why I repeat all these things. And I do this typical operational way of teaching. I told it before. And also it is useful anyhow to know these classical ideas, because if you do normative prescriptive work, you have to do that anyhow. What I like most about the behavioral approach is if you study the differences between the normative and the descriptive models, there you can see where you can help people make better decisions. Then of course you have to know the classical, the normative models. So surely it's a good thing studying them. Well, the previous meeting, I tried to convince you that expected value maximization is a normative, rational thing to do if the money amounts, the stakes are moderate. Sometimes, not very often, but sometimes in our life, we have to take very important decisions, and then there can be big stakes. Like if you buy a house, what mortgage you should take, if you want to invest your money, if you decide on health insurance for all the rest of your life, then big stakes are involved. Then the theory of the previous meeting was not very useful. It comes to it that in many decisions we get non-quantified outcomes. For instance, if we must decide between risky medical treatments, health states may result, like being blind, being deaf. They are not quantified. We cannot even define expected value. We cannot define the relativity preference condition. So then again, you need more general theory. In fact, many of you will know the concept of utility. In the previous meeting, we assumed, or in fact, we derived linear utility. Today, we're going to generalize by allowing non-linear utility. That makes a few things more difficult. However, we don't want to be too hard on ourselves. We want to make life easy to begin with, to handle these difficulties in a good way. Other things we make easier. Therefore, I'm going to assume today, I'm going to work for a while with a toy example again of last week. No rain, some rain, all rain. Ice cream or hot dogs, both or none you take with you. That was the example. I'm going to assume, to make things simple, today that we know probabilities. Probabilities of events are given. For instance, in this situation, we assume that no rain has probability P1, 1/4. Some rain, event S2, has probability P2 is half. All rain, event S3, has probability P3 is 1/4. That probability is non-negative, the sum to 1. That's happening here, so that's good. And we assume we have extensive statistics. Everybody agrees on these probabilities. Everybody uses them. They are objectively given. That's a deviation from the first meeting. Now, if we look at the first choice option that we had, the merchandise to take along with us, ice cream, we know that ice cream, it can give us outcome 400 if there is no rain that day. And we know that happens with probability 1/4. We know outcome 100 can happen, this event, probability half. And we know all rain, probability 1/4, gives -400. So we know that these probabilities and outcomes result from X. Let me put brackets around it. So I denote it this way. X yields this probability distribution over money amounts. And note notation, I write a probability column, money amount, comma, and etc. So that's a notation that I use in these presentations. Now I look at the second option, choice option, that the second merchandise being hot dog, and I immediately write in one blow the whole probability distribution. It gives, if there is no rain, 1/4 probability, it's -400, half probability 100, quarter probability 400. Same reasoning. Taking nothing with you gives you nothing with probability 1. You know for sure you get nothing with probability 1. Taking both options, both merchandise with you, then you know with probability half, this happens, you get 200. The other events together have probability half, so with probability half, the outcome is 0. So that's the probability distribution generated by taking both with you. In decision making under risk, and that's in fact what we're going to do today, what we're going to assume today, we assume that only the probabilities of the outcomes matter, not the events that generated them. The only thing you want to know about no rain, some rain, all rain is what the probabilities are, and that's it. If you receive outcome 400 with probability 1/4, that's all you want to know. Whether it was raining that day or whether it was sunshine that day, you don't care. So the events have no intrinsic value, no ethical value, as the famous researcher Ramsey would say. Anyway, the only thing that matters of events is their probabilities. That's a typical assumption of decision making under risk. Now, the things that we choose between are then probability distribution over money, and I use the term prospect here, and I didn't say it in the first meeting, but throughout this course, I use the term prospect for those things that you have to choose between. There can be different things in different meetings. In the first meeting, last time, you had to choose between your merchandise to take along with you. We could identify them with triples from the real number, R3, or elements from R3, specifying for each of the three events how much money you make there. So then prospect we could say they were elements from R3. They were merchandises. Today it's different. Today, decision making under risk, we only care about the probability distributions resulting. So that's how we denote the options, the merchandises. That's what we choose between. We're choosing between probability distributions over money. Another term, if I want to be explicit on that, is probability distribution over money. Then I also use the term lottery. Today we are choosing between lotteries. Lottery is a probability distribution over money. And then, so many terms, but that's how it is. Now, maybe I'm going to ask you a question and you can pause the video and think for a moment. If you compare options X and Y, ice cream and hot dogs, you can see something remarkable. So take a minute, and if you see it, and then come back. Okay, I assume you thought about it as long as you like. Now you're back again, and you see that X and Y, they provide the same probability distribution over money. This is the same probability distribution as that. Each time 400 has 1/4 probability for both, minus 400 also 1/4 probability for both, 100 probability half for both. They are the same probability distribution. So decision making under risk says they are identical for every purpose that we can think of. They are equally good. We in fact identify them. So in decision under risk, hot dogs is identical to ice cream, so to say. What I mean, of course, is they give the same probability distribution over money, so we can treat them as identical. That is the condition that defines decision making under risk. We kind of forget about the events that generate the outcomes, but we only write the probability distribution over money. We don't care what the underlying events are. That assumption that you can do that is non-trivial, need not always hold. For instance, in our toy example, it means if you get 400, you don't care if it was under sunshine or under rain, that weather, you don't care about it. You only care about probability and outcome. That need not always hold in practice, but we're going to assume it today that it holds. That's what happens with decision under risk. That's what we are assuming today. Some notation. Here is a probability distribution over money. With probability P1, it gives you X1 euro. With probability Pn, it gives you Xn euro. And probability and non-negative sum to 1. That is implicitly understood always with this notation. Another way to denote it, often using figures, is like this. Then this circle, I call it the chance note. Here the idea is the goddess of chance decides if it goes up or down or whatever. If it goes all the way up, with probability P1, that happens, you get X1. With probability P2, the one below, you get X2. With probability Pn, she chooses to go all the way down, you get Xn. That's another way to denote the lottery, the prospect. Here is if there are two outcomes, we sometimes have a short notation. Here, only alpha and beta can result. The probabilities they add to 1, of course. This is the shorthand notation. We write only the two outcomes, and you have to remember the probability is a subscript. You have to remember that this is the probability of the first outcome. The second outcome result with 1 minus that probability, of course. So that's shorthand notation for two outcome prospects, lotteries. if there's only one outcome, if the outcome is alpha, like €100, then that means you get it with probability 1. So if alpha is €100, we say that's the same as getting €100 with probability 1. We identify outcomes with numbers with the probability distribution that gives them with probability 1. This is in the same spirit as what we saw in the first meeting. In the first meeting, we also said the money amount outcome means you get it for sure. Then it meant you get it if no rain, if some rain, if all rain, you always get it. So 100 means the triple 100, 100, 100, that you get 100 no matter what event happened, no matter what the weather is. So it's the same. This is in a way the same as in the first meeting. An outcome means you get it with certainty. Now, preference condition, risk aversion, general dislike of risk. Let us look at a lottery, probability distribution over money. And here I write, and you see that is the expected value of that lottery. Imagine, so this means, this is a real number, money amount. This means you get this money amount for sure. That notation here. If you must choose between those two, risk aversion says you rather have that expected value. Well, they have the same expected value, of course, but the here one, you get something with certainty. Here you have uncertainty risk. So other things equal, you prefer the certainty. That is what risk aversion is. You always prefer the expected value of a lottery more than the lottery itself. If you're always indifferent, we call it risk neutrality, then you are an expected value maximizer. And the other way is risk seeking. If you rather take the risky option than the sure amount, then we call you risk seeking. I want to call your attention to this. I'm giving these definitions, these preference conditions, that's what they are. I give them prior to having defined any theory. They don't, I'm not specifying any theory, but they are just empirical conditions. More of that to come later. Next topic will be, I'm going to present to you the St. Petersburg paradox, the famous paradox that falsify expected value maximization. That was historically also a reason why people wanted to do something more general, the topic of today, but that will be the next recording. I'm going to stop the recording here.